Hello everyone, this is Dr. Webb, and in this video we are going to be bringing abstract algebra to order. So order for a group means the same thing as order for a set. It's just the number of elements of the set. So given a group, its order is how many things are inside of it. If it's an infinite group, then that order would be infinity. If it's a finite group, we'd give the number, the natural number that says the number of elements. So notation, usually for order of a group, we will do sort of absolute value around the group, same as we often do for sets. And for example, how many elements are in D4? So D4, this is the number, this is all the symmetries of a square. And for D4, there are 8. So the order of D4 is 8. For something infinite, if we wanted to do what's the order of the integers, we just say that's infinity. So what if we want to talk about the order of an element? This is something that doesn't really apply to sets, so this is a different idea. The order of an element, G, in a group, is the smallest n, it's the smallest natural number, such that when I apply that element to itself n times, I get back the identity. And if there's no such n that makes this true, then we're going to say that G has infinite order. Okay, and the notation for this, in Joe Galligan's book, he uses the absolute value signs around G, but what I more often typically see for order is the ord of G. So ORD of G is used to talk about its order. Okay, and so let's take something, so we talked about D4, it has 8 elements. Let's take the rotation by 90 degrees of that, and let's think about what its order is. So let's work out what we get. So we have R90 by itself, and then if we do R90 squared, so that's, you rotate by 90 degrees, and then you rotate by another 90 degrees. Well, that's going to be R180. If we did R90 cubed, well, so that would be 90 degree turn, and then another 90 degree turn, and then one more 90 degree turn. So 180 degrees plus another 90 degrees gives us 270 degrees. Let's write that as R270. And then if we do R90 4 times, well, so 3 times is 270, and then we do it one more time, well, that would be a full 360 degrees around, which leaves us back where we started. So we're at our identity for the group R0. And so how many times did we have to apply R90 to itself to get back to the identity? Well, it's 1, 2, 3, 4. So we would say the order of R90 equals 4. Okay. So if you take any finite group and you take an element of that, then every element in a finite group has finite order. So if you're in a finite group, you take any element in it, you apply that element to itself enough times, you're going to get back to the identity. And so this is an important fact about finite groups, that you take anything inside a finite group, you keep applying it to itself enough, you get back the identity. Okay, so why is this true? And so this proof really relies on the pigeonhole principle. And so let's just start off with, we have some G and G, and we're just going to start looking at listing out all the powers we can get, going on forever. Now, since we can keep going these powers higher and higher, by closure, each of these are inside the group, right? But the group only has a finite number of things total. And so if I have an infinite list, all of things in the group, but there's only finitely many things in the group, that means at some point I have to be getting repeats in this list of powers. And so since the order of G is finite, less than infinity, by the pigeonhole principle, I have to get a repeat somewhere. So there exists some n and k that are not equal to each other. Such that g to the n is equal to g to the k. Okay, so let's suppose, since n's not equal to k, let's suppose that n is bigger than k. Okay, and so we can think about this as being gn equal gk as being g, I can pull k things out, and then I'd have g to the n minus k things left is equal to g to the k. And now by cancellation, I can think about this g to the k as g to the k times the identity. And so then by cancellation, I can cancel off the g to the k's because they're both on the left. And we're left with g to the n minus k equals the identity. Okay. And so this tells us that there is some natural number n minus k, such that we do g to the n minus k equals the identity. And so then it doesn't mean that's necessarily the order, but that means that it happens once, and so we could just check all of the previous powers of g to see if any of those were actually the identity before then to find the smallest one. And so this is enough to establish the theorem. Okay, so let G be a group. We're going to take some element of this. Then a special set that we're going to think about a lot of times, which we're going to call this sort of kind of angle brackets A. And what angle brackets A is going to be is it's the set of all the integer powers of A. So again, we're thinking about the order of the group being multiplication. So this is all the different ways you can apply A to itself. And we're going to make a couple special definitions in here. So when we say A to the 0, we're really talking about the identity. So we're including the identity into this set. And if we're talking about A to a negative power, what we're really thinking about is we're taking the inverse of A and raising it to a positive power. Okay, so A to the minus 1, that's the inverse. A to the minus 2 is really the inverse of A squared. Okay, and so in this set, we have forced the identity to be in there and the inverse of A to be in there and all the powers of the inverse of A to be in there. And it turns out that by doing this, we have made this set a subgroup of G. Okay, and that's a theorem. Because it's a subgroup of G and it's made by all the powers of A, we usually call it either the subgroup generated by A or also possibly the cyclic subgroup of A. And so cyclic groups and cyclic subgroups, that's what we're going to be talking about starting in the next video. But this is just one brief introduction to what these look like. Okay, so why is this a subgroup of G? And proof of this, we can do this with the one-step subgroup test. Okay, so remember in the one-step subgroup test, all we need to do is that if we take some, so we need to show that for any x and y in this set generated by the powers of the set of all the powers of A, that x times the inverse of y is in there as well. Well, if x and y are in there, and this subset is powers of A, well, then that means that x is equal to an for some power n, y is equal to ak for some integer k. And so then if you have y inverse, that's going to be just the same as a to the minus k. And so again, that's in the same power. That's an integer. And so then the idea is, well, what's x y inverse going to be? Well, it's a to the n times a to the minus k. And even though, we're treating this like multiplication, the exponent rules here really apply the same based on how we defined what negative powers are. And so at the end of the day, this is just going to be a to the n minus k. And so I'm skimming a little bit over, what if a is negative and k is positive, or n's positive and k is negative. All of that, it all ends up working out exactly the same as you would expect it to. And so you're always going to end up with a to the n minus k. And since n minus k is an integer, this means that a to the n minus k is in there, and we are done. That's the end of the one-step subgroup test. Okay, so let's go back to our rotation by 90 degrees in D4. What is this subgroup generated, this cyclic subgroup generated by it look like, or the subgroup generated by R190, R90? Well, so let's not forget the identity. That's sort of the 0th power. And then it has R90, and then we already showed that R90 squared is R180. And R270 is R90 cubed. And then after that, we saw that we got R0 again. And then if we apply R90 again to this, we just go back to the beginning again, right? And so if we start looking at the positive powers of R90, we're just going to be cycling through R0, R90, R180, R270, and then go back to R0, R190, etc., etc., etc. Now, if we're looking at the inverses, so the inverse of R190 is R270, and then if we start taking the powers of R270, R270 squared is R180. And then R270 cubed is equal to R90. And then if we raise it to the 4th power, we can work this out. 270 to the 4th. If we work this out, we get back R0. And then to the 5th power, it would cycle back to R270 again. So the powers of R270, the powers of the inverse, also just give us all these rotations. So what do we get this to be? Well, it's just the subset of rotations. So R90 generates the subset of the subgroup of rotations. I should have put 180 there. A little bit out of order, but it's just a set. Okay. So let's think about some other examples of subgroups generated by a single element. So what if we started off with R with addition and took 1 and just think about what happens when we apply 1 to itself with addition over and over again? Well, so it's going to have 1, and then I can keep adding 1 to itself. So it'd have 1, 2, 3, 4, 5, 6, 7, etc. It would have 0, because not applying it at all will give us 0. But also it would have its inverse, and so it would have -1. And then if we start adding -1 to itself over and over and over again, we get -1, -2, -3, etc., etc., etc. So what do we end up with all these possible ways of using 1? Well, we get the integers out of it. So the subgroup generated by 1 is the integers. What if we started with the integers with addition and thought about starting off with 2? Well, so 2, it would have the identity, which is 0, and it would have its inverse, which is -2, and then it would have all the ways of applying those to each other. And so you'd have 2 plus 2 is 4, plus 2 is 6, plus 2 is 8, etc., etc., etc. -2 minus another 2 is -4, minus another 2 is -6, minus another 2 is -8, etc., etc., etc. So what do we end up with at the end? All of the even integers, right? So the subset generated by 2, the subgroup generated by 2, is the even numbers. So then what about I? And so C star, here, this is not notation I don't think I've used before, so let's be clear on this. C star, this is shorthand for saying C remove 0, and our operation is going to be multiplication. Okay, so C star is you take C, you remove 0 out of it, and then you include in multiplication. So if we have I, the complex number I, what's the subgroup generated by it? Well, if we go through the powers of I, we get I, and then I squared is -1, and then I cubed is -I. So call that I cubed here is -I. And then if we apply -I times I, that would be minus times -1, which gives us back 1. And so it just starts cycling back before. And so note that I cubed, which is -I, this is the inverse of I. Okay. And then lastly, if we start with any group, the subgroup generated by A is going to be equal to the subgroup generated by its inverse. And you can see this just by doing a quick double inclusion, that if you have some A to the n, this is obviously some general element of the cyclic group of A. Well, you also can think about that as being A inverse to the -n based on our definition. And so it's in the subgroup generated by A inverse. On the other hand, if you have A inverse to the k, this is going to be the same thing as A to the -k. So it's in the cyclic subgroup generated by A. And so A to the n, that represents a general element of brackets around A. A to the -1 to the k, that's a general element of A to the -1. So by double inclusion, anything in one is in the other. And so the sets are equal. That is all for this video, and I will see you again soon.